Hello and welcome everybody to your week 2 of lockdown 2021. This will be for week beginning 18th of January 2021, and we're going to move on this week and go on to continue talking about semiconductors, but take it a bit further and talk about applications of semiconductors and how we use them in circuits. Now this week there is a bit more questions to do this week because we're starting to tick all the boxes to allow us to answer more questions. There are more questions in your problem booklets. There's also a really good BBC Bite Size quiz you can do and a whole load of notes there, and your textbook's really useful this week as well. As with last week, I'm going to give you a Microsoft form on Thursday, which will be a bit more than last week's form and gives you a lot more questions, and we'll also be giving out the semiconductor homework, but I'm going to give you about a week to do that. I'm probably going to give it out on Wednesday for handing in next Wednesday. Your class teachers are quite keen to take work from you for review. It just shows us you're making an effort, and we'll provide some feedback on it where they can. So, the different types of semiconductors. So we talked about what semiconductor was last week, and this week I'm just starting off by explaining that semiconductors are actually found in nature, just like any other element, any metal. They can be mined, for example, but they have to be in a particular kind of structure. So if they are found in nature, they're known as intrinsic or pure semiconductors. Silicon is a semiconductor. You may be familiar with Silicon Valley in terms of talking about America and where a lot of technology is made, because silicon is the kind of foundation for modern day electronics. But silicon, to be a semiconductor, has to be in a crystal structure and as a solid. Now, if you take a piece of wafer silicon, like you can see in the picture there, and heat it up to a high temperature, it will conduct electricity. But the amount of energy required to allow it to conduct is not really efficient. You need quite a lot of energy just to allow a piece of silicon to conduct. Quite a lot of heat to do that. If you watch some of the YouTube clips that I've got attached to the assignment, you'll see a demonstration of this. Now, in order to keep that property but lower the amount of energy required, what we do is take that silicon and introduce other elements into its structure. And what that does is it changes the energy bands. It reduces the size of the energy band, meaning that smaller energy amounts can cause it to conduct electricity. Now, when we introduce another element into the structure, this is called doping, and it reduces that energy gap, like I said, and we can take an intrinsic or pure semiconductor and dope it to produce two different types of semiconductor, either an N-type or a P-type semiconductor. And I'm going to go on and explain what an N-type is and what a P-type is, and then what happens when we put them together, and what we can do with them when we put them together. So the first type of semiconductor we're going to look at is called an N-type. This one so we take the silicon, so here we've got silicon as an element, and we would dope it, which means add in another element. In this case, we're adding in an element SB. Now, I have to admit, I don't know what SB is. You could go look up what SB is. So, in this diagram, silicon has 4 electrons in its outer shell. So, 1, 2, 3, and then one of these two belongs to silicon. And there's 4 in each of these silicons. Now, this SB element has 5. So, it's got 1 bonding with this, 2, 3, 4, and then it's got 1 spare. So the silicon has 4 electrons in its outer shell, and the SB element has 5 electrons in its outer shell. 4 of the silicons bond with the 4 of the SB element, leaving this 1 extra electron. That's we call a free electron. Now, if we think about it in terms of band theory, in terms of this diagram down here, then you've got the extra electron produced is just below the valence band. Just below the conduction band. It's called a valence electron because it came from the valence band. It's just below the conduction band of the material. This means the energy required to raise this electron into conduction band is lower, and the resistance of the material has been lowered. So this energy jump required to get that electron into conduction band is smaller, meaning that it doesn't require as much electron to let it conduct electricity. Now, one of the big misconceptions about N-type and P-type semiconductors is that they are negatively charged for N-type or positively charged for P-type. Now, that's not correct at all, and the reason we call them an N-type and P-type is that because in an N-type semiconductor we say that the charge carriers are negative. In a P-type, the charge carriers are positive. That's where the N and the P comes from. It's not negative and positive overall charge that they have. So overall, there are still, and if you look at the diagram, there's still 4 electrons and 4 protons in the silicon, 5 electrons, 5 protons in the SB element. So overall, they don't have a charge. They're still neutral, and they don't have a charge as such. So they're still neutral overall. And like it said at the bottom there, the free electrons can also be referred to as negative charge carriers. So this moving free electron, which is negatively charged, is the negative charge carrier in an N-type semiconductor. Now, P-type semiconductors is the opposite things happening here. We take a silicon with 4 electrons in the outer shell and we dope it with another element that has 3 electrons in its outer shell. So in this one, Si is our silicon, and B is the element with 3 electrons. Now this here is a hole, we call it, and impurity creates a hole. So we have this space where an electron could be, and it's a space that an electron could fill, we call it a hole. So a hole an electron could be in. If you look at it in terms of band theory down here, this extra hole is just above the valence band. It means the energy required to raise an electron out of the valence band is low, and the resistance of the material has been lowered. So overall, we have lowered the resistance of a P-type semiconductor as well. Again, overall, there's still a balanced number of protons and electrons, sorry. So therefore, it has not got any charge. And we say that these holes are positive charge carriers. Now, it takes a wee bit to understand, but if you get negative charge flow in one way, we normally have positive charge flow in another way. But it's the P-type has positive charge carriers, and that's what these holes are. They are positive charge carriers. Right, we're going to put these together, and we're going to create a p-n junction. Now, a p-n junction is basically just a P-type and an N-type put together. And a p-n junction is basically a diode, and you're familiar with diodes from National 5. You should be familiar with a diode in that they conduct electricity in one direction, but don't in the other. So we're going to look at what happens when you put a P-type and an N-type together without attaching any circuit to it. And then we're going to attach the circuit to the p-n junction, and with current trying to flow one direction and current trying to flow another direction, and see what happens. So when you put a p and n-type together, you've got these free electrons in the n-type, and you've got these free holes in the p-type. What happens here is these electrons jump across and fill the holes, and they only have so much energy to jump across a small distance, but there would have been negative electrons here and holes here, and the electrons have jumped over into these holes and filled the holes. So there's no holes available here and no electrons available here. So really there's nothing that can allow charge to flow. No negative charge carriers, no positive charge carriers in this area in the middle. And this is known as the depletion zone, or the depletion region, or the depletion layer. And there is no free charge carriers in that area. So that area there has basically become an insulator, because there is no ability for any extra charge to flow in there. It's not a semiconductor in these materials here. So it's the electron has jumped across the gap at the boundary and filled in the hole. So we refer to this as the positive and negative charge carriers have combined to form an electron-hole pair in this side. This creates an area near the boundary of the two materials where no free electrons or holes, which act as an insulator called depletion layer or depletion region. So if we want this p-n junction to conduct or do anything for us, we're going to have to get rid of this depletion region or depletion layer, or else it won't conduct at all. And if we're not careful or do it the wrong way, we might actually make this depletion layer bigger. So we can connect up a p-n junction in two ways. Connect up a diode in two ways. The first one is known as forward bias. Now current is coming from the supply round here, and so electrons are coming around this way, and negative charge is getting pulled around this way. So when a diode is connected as shown in the diagram, it's known as forward bias, and the current will flow in forward bias. And it's flowing from N-type to P-type. There's actually current flowing in a circuit because the PN junction will conduct in this forward bias. So electrons are forced into the P-type and forced into the N-type and pulled from the P-type. Electrons in the depletion layer are moved by the electrons coming from the supply. The depletion layer is destroyed and the PN junction diode conducts electricity. Now, this is an older way of explaining PN junctions, but I think it's still very useful at understanding visually how the electrons coming in this side push against the free electrons in here, forcing them to destroy the depletion layer and jump across the holes. Now, I've got this idea of little electrons jumping between the holes. You know when you get that game with the marbles and they jump through the holes in the game? That's the kind of image I get as the electrons jump across the hole, get pushed in here, and then jump across the holes through the P-type and then back around to supply. As I said, that's not really the way we should be explaining it now, but I find it really useful to help you understand how it works. Band theory is how we're supposed to explain it, and I'll go on and explain it as I explain an LED to you near the end of the slides. So, direction of current flow is this direction, and this is the circuit diagram of a diode. It would be conducting electricity this way. The way I used to say is that if you consider this as an arrow and this is a wall, you can't fire arrows into walls, but it does go the other way. The other way didn't really work. I tried an analogy with a balloon and a hole and try to make a hole in a balloon, but that didn't really work. It's fine. So, we then have reverse bias. So all we've done here is turned the supply around the other way. Electrons are getting forced out of supply this way and pulled into supply this way, but we don't have current flow. Now, this is known as reverse bias. In reverse bias diode, electrons in the supply are forced into the P-type, filling the holes. So we have electrons coming around here and filling all these holes. So again, if you think about the little dish with all the little marbles on it, all these holes are being filled. So if there are no holes to allow the charge to jump across the gap, then it can't conduct electricity. So the holes in this P-type are all being filled by the electrons jumping in from the negative side of the supply. So this depletion layer in the middle actually gets bigger, becomes more of an insulator. In the N-type, the electrons are getting pulled round that way, so these free electrons are actually getting pulled in by the supply, and they're no longer free, and the depletion layer again gets bigger. So by filling the holes and removing the free electrons, the size of the depletion layer is increased. The increased depletion layer increases the resistance of the diode, making it more of an insulator than it was before, and in reverse bias, no electricity is conducted. You can't allow, current does not flow across the PN junction in this case. Again, it's an old way of describing it, and for band theory explanation, we'll go on and do it for LEDs. So, here we go. This is an LED. This diagram down here refers to what an LED in terms of band theory and how it conducts. Now, I'll explain what an LED is first of all, and then we'll discuss the band theory behind it. So, in all forward bias diodes, the free electrons in the N-type are given energy by the supply to enter the conduction band of the P-type. So, forget this is light at the moment. If we just think about this as just a PN junction, we've got these electrons that are coming from the conduction band of the N-type, these free electrons, and they're given enough energy from the supply to get pushed forward. Now they go across the gap. Now the boundary between them is somewhere in the middle there. In fact, the boundary is probably just there on that line there. So these electrons are given enough energy to cross the boundary into the P-type. Now they cross the boundary into the conduction band of the P-type. They don't want to be there, and they drop back down and they fill the hole inside the P-type. So electrons come along and fill the hole. And that drop there, that drop in energy band, that drop in energy level, releases some form of EM radiation in all diodes. Now, so the drop between bands, between energy levels, and the combining of electron and hole releases energy in the form of an EM wave. In standard diodes, EM wave is infrared, it's heat. That's why diodes heat up. That's why modern day electronics heat up. That's why you need a fan in your computer. That's why your phone heats up when you use it too much. It needs to be cooled down. So there's a lot of heat getting produced in diodes, and that's why electronics heats up, and because they're releasing this heat. in a specific type of diode known as an LED, here's the circuit symbol here, that EM wave is in fact light, and because of the material that this PN junction is made from, because of the energy drop, we can release light rather than heat. We can change the colour of this light by changing the amount of energy released as does that energy level drop. Now, there is a way of calculating exactly which colour and not exactly the size of the energy, and we're going to go and talk about that in a few weeks to do with energy, Planck's constant, etc. So if you're doing any past papers on this and it asks you to work out the wavelength or frequency of the energy released, and it talks about energy levels and giving them a value, then you can't do them just yet. You need to wait until we do that theory, probably not next week, but the week after. So this diagram you need to be familiar with. It's conduction band, valence band in the N-type, conduction band, valence band in the P-type, and the electrons are given enough energy to enter the conduction band in the P-type, then drop, combining with the hole, and it's that drop that releases the EM wave. Now, the second diode, or second PN junction that we're going to look at is known as a solar cell. Now, solar cells are essentially LEDs in reverse. Solar cells are used in solar panels to produce electricity. So instead of energy going in the form of electricity and light coming out, as you would in an LED, we get light coming in and electricity given out. So in solar cells are special PN junction diodes called photodiodes that behave like LEDs in reverse. An LED, light energy is released and electron drops between the conduction and valence bands. So just in the last slide, you've got conduction to valence band, the energy is released. And what we have here in a photodiode is you've got that electron hole pair, and they've been given enough energy by the light to separate. And if you separate electron hole pair, you allow these free electrons to go one direction and the holes to go in the other. Positive charge carries one way, negative charge carries the other way, and it creates a current flow, creates a potential difference. So in a photodiode, light energy is absorbed by the electron hole pair, which separates the electron hole pair and raises the electron from the valence band to conduction band. This moves the electron towards the N-type, creating a potential difference across the photodiode and current flow. This is known as the photovoltaic effect, and the photodiode is operating in photovoltaic mode. So a photodiode being in this arrangement is and giving you electricity out is in photovoltaic mode. The greater amount of light, the greater the voltage produced. So if we put more light in, more light energy, we get more potential difference or greater current. And this amount of light is referred to as irradiance. Now we're going to talk about irradiance in more detail next week. It's just to give you that word if you see it in a past paper question, what irradiance is. So irradiance is just more light. So if it's increased irradiance, then it's increased light level that we're looking at. Okay, that does us for this week. As I said, there are questions to have a look at. There are going to be a form quiz, and there's also going to be BBC bite-sized work to do. And as I said, you're going to get semiconductor homework on Wednesday. We're also going to offer supported study for hire this week, and that's going to be on Thursday at 9 o'clock with myself, Mr. Long, and Thursday at 2 o'clock with Mr. Huggins. And I'll put all the details of that in the assignment and let you see when you can join us for support study if you just want a bit of face-to-face question and answer it. Okay, any other questions, just direct them towards your class teacher on the Teams or email as you have been, and hopefully you won't have any too many problems. Any issues, please let the class teacher know.